Oh, hi. I guess we should start. I think you would notice I put up the homework one in the blackboard. So you'll be due next Friday at the end of the day. So you probably have 10 days or so, 9 to 10 days to finish it. And it's just only 3 questions. The first question is basically calculating summary statistics that we have learned, and then calculating covariance and correlation. And the third question would be just basically ask you to do the Excel. So try to tell me the formulas that are required to do calculation. Okay. So the first homework is easier. So don't think this is that easy for the rest. Don't underestimate the difficulties, because it will get more difficult, but I think you can manage. It's not easy. So what's the goal today is we will finish this probability, and then hopefully we have some time to talk about random variable. Okay, so let us very briefly review what we have learned on Tuesday. So the very first thing is go back to the definition of probability, just to remind you that the probability we start from the beginning, that start actually 300 years ago, is about defining probability by random experiment. You repeat things and then try to look at the ratio. So by definition of this is already the probability must be between 0 and 1, right? And the probability of the whole sample space must be 1, right? So that would be the thing you do, right? And we know this is going to hold for our axiomatic setup, right? We define probability also from 0 to 1, and then the whole sample space is 1. Okay, so what is the main thing different from what you learned from the classical idea about the ratio is the axiom 3, okay, which is saying that if an event is can be decomposed into mutually exclusive outcomes, right? The probability of that event will be the sum of probability for each outcome. Okay. In the other word, when you look at probability of certain thing, you can cut it into in separate pieces, and you can calculate probability for each part. Okay. Some of the parts will be same as the whole. Okay. So basically, what he said is probability of the whole is same as sum of the parts. Okay. So that's what it means. And the main thing is about this also extend when you have infinite cut. Okay, so that is the main thing. And just to remind you, some terminology is how to define intercept, how to define union, how to define complement. That tells us what is mutually exclusive, what exhaustive, and what is partition. Okay, and based on the 3 axioms. And here we come the complement rule. Okay, probability of certain event will be 1 minus of the probability of its complement. Okay, and this can generalize into partition, right? If you have an sample space, then you can partition into different parts. Then it should be the same idea. Add up will be 1. Okay, and there is called addition rule that try to make us understand how union and intercept are related, right? And this graphical is very simple, right? Just this big red circle plus this blue circle, because it overlap the pink one, take it out, will be equal to this I don't know, this snowman shape style. Okay, and other rule we know is we call the total probability rule, that imply if and even A can be decomposed by the intercept B and its B complement. Okay, note that B and B complement is a partition of sample space. Okay, so basically the idea is you partition sample space, and probably A will be the sum of all the parts intersect with each part of the partitions. Okay, so that is what it means, right? There's a partition sample space, B and B complement, so you can have A intercept B complement and as well as A intercept B. So basically divide them in two parts. Okay. And in general, this also hold, as I said, is partition also hold true. That's a total probability rule. And then we learn this odd ratio. Odd ratio, okay, is trying to say if you have a fair bet, okay, which you should know more clear in the next class. But if you try to bet, then you expect not to make any gain or any loss. So that means that you are indifferent between being a gambler or a casino in this scenario. Okay, and if you believe the casino is competitive, okay, so by looking at the odd ratio, you can infer the probability. Okay, what do I mean by that? Is if I go to the horse racing in Hong Kong, right, and there are odds for each horse, right, and then you can use the odds to infer what's the probability that a particular horse would win. Okay, so that would be one way to use the market in terms of probability, and this is sometimes used in the financial market, right? People use this to infer whether interest rate go up and go down, whether certain event happen or not. That is possible to do that. Okay. And we come to a little bit more difficult. From that on is we need to define what is conditional probability. Okay, is suppose we know certain thing happened, what would you learn from that? Okay, and that would be very important because we learn how things changes. Okay, so here is a probability of event A given B had happened will be a fraction where the numerator would be the intercept because we know B had happened. So only A intercept B will be relevant because A intercept B complement will be irrelevant, right? And you have a denominator has probability B because probability must be between 0 and 1. Okay, so you must divide it to make everything between 0 and 1. Okay, although we can prove it, but we just take it as given. We know the justification, but we're not doing any. We just take it as a definition. Okay, so of course, if you look at some advanced textbook, they will try to show you why this will make sense. But for our purpose, I think that would be sufficient. Just take it as definition rather than a proof. Okay, so this example we illustrate kind of telling you why when the sample space shrink, that is how you arrive the same answer. Okay, so this is more or less same as the proof, but if you make everything very general, this is the proof. But of course, that will be the idea. Okay, so after that we learn by swapping the denominator for this definition. You multiply product B for both sides. Okay, and you end up with this, right? A and B is A given B times B or B given A times A. Okay, so which one to use depends on scenario, which is easier, depends on situation. But it doesn't really matter which you conditional on, just you multiply by the probability. And then this the graphic. So next one is this formula, which is useful. Actually, use it when we do the base rule when you have a denominator. that is mainly most of the time you use it for the denominator purpose, right? So probably A will be A and B complement, and you can use the multiplication rule again, give you this formula. And if you look at some textbook or online, sometimes they will call this, instead of the first one, they will call the second one is the total probability rule, but I guess depends on which one you like, but the same thing, right? Because with the multiplication rule, you get the same expression. Okay. Now the last one is the independence. Okay. The definition is rather simple. If probability A given B is same as A, so which means that having B or not doesn't really matter. The second one is B given A same as B, whether A happen or not doesn't really matter. Okay. Turn out it's easy to see that if this hold, this would hold, and three of them are the same, right? The intercept when the independent will be same as they multiply. Okay. So this looks rather simple, but this is very useful. Okay. Turn out that we really rely on this one to do things much easier. Okay. And this is actually later we relied on what we call random sampling, right? That's later you see at the topic 4 or 5 talk about we do collecting samples, and when we collect and we assume random sampling, which means that each sample is drawn randomly. Okay. And things become much easier because the intercept is same as just multiply things together. And this is the main thing that we rely on from this to the rest of our class. Okay, without this, then our life will be very difficult, right? Because if not independent means it's not different, not the same, right? So we have to say what's probability you get this draw and the other draw together is, things is very complex. For now on probably it's difficult to understand, but hopefully when you go to the later stage of a course and then you realize that this is a very important thing that will make our life much easier. Without this, then very difficult. Okay. If you try to, when you draw the sample, if each sample is related, okay, things become very complicated. Okay. And it is often the case sample is not independent. Okay, it's not surprising. It depends on how your sample method. One main famous example that you try to read the textbook, they will tell you that in the US election, in old days, people try to do poll. They ask whether you support candidate A or candidate B. And I think 30 to 40 years ago, when they try to do it, is we don't have internet at that time. People do make a call. Okay. And when they do the call, then people pick up the phone and ask to support A and B. And the historical event said, one say, okay, there's one event that all the survey figure out that, or the poll said, candidate A is going to win. Okay. But turn out that the surprise B won. The reason is being that actually those who at the time had the phone are rich people, right? And actually those who don't, and then you left out is relatively less rich, and in that case you just omit a lot of stuff, so which means that when you draw a sample, it's not independent, right? You're particularly focusing on a small particular group, and in that case then you're not doing a right sample, right? It's not independent, right? So that means this is some issue there, but just this technical term have to realize that independent and mutually exclusive are completely different, right? And when you're mutually exclusive, then it's not independent. When you're independent, it cannot be mutually exclusive, right? So these two are mutually exclusive, right? If you try to confuse yourself, So the very last one is Bayes' rule. So this is so important that let us go over it again, because you have to, when the assignment 2 comes out, which I'm too early to say it, but you have to do this, right? And I said this is the probably the single most important thing you learn from this particular topic of slides, because this, if you ever use probability in the future, this is the one for sure you will be facing it again, because this is how data make us smarter, we are more informed. How we change our view is based on this. Okay, we have some idea how things work, and after observing some data observation, and this data you adjust accordingly. Okay, and this is actually what happened, right? The COVID-19 pandemic now is we have to test, or medical test, right? Same a lot of time. You just, and medical test is not 100% accurate, right? You might have false negative and false positive, right? In that case, you have to be very careful. If the test is fully accurate, then you have a problem. Okay. So that's why we need to learn Bayes rule. So the Bayes rule or Bayes theorem is like this. This looks nothing, but if you replace this, it's just the numerator is just basically the A intercept B, right? We just replace the numerator by multiplication rule. Okay, so there's nothing deep in this proof, right? The behind just the numerator again is A intercept B, right? So why this is important? Because the important thing is, look at here again, is you swap AB from the original data. Okay, so that is the main key of this. Okay, so now let us look at the in terms of graphics. Okay, so you have something like, suppose in this way you have A and A complement, right? And after A you can have B and B complement, B and B complement, right? So what we want is, we want to have is what happened is, what we want is we have probability A given B. Okay, so we observe B, what is probability of A, right? So that's what we want to find. Okay, so that how you're going to do is, if B happen, okay, that means that actually only these two branches are relevant, right? Because the other two cases are unrelated B, right? So what is probability A, right? Will be just the ratio, because the sample space is only this one. Okay, so basically the Bayes rule will tell you, okay, you will just have this, let's call this X. Okay, let's call this Y. Okay, this is just X over X plus Y. Okay, because the whole sample space now is X plus Y, right? Now only relevant, you say what happened A, right? It's just the X. Okay, so that is exactly this graph showing you why we have this formula, right? So we observe B is only these two branches relevant. Okay, what is the relevant to A? Just the upper branch. Okay, so basically Bayes rule in this diagram, if you want to think graphically, it's just the first branch over sum of the first and the third. Let me repeat, is this a fraction? Numerator is the first branch, the denominator will be this first and third. Okay, because the second and the fourth are not relevant, because you know B had happened, so B complement is not there. Is that clear? Why we have this? Is that okay? I hope this is clear why we have this formula. Okay, so that's why this over sum of these two, and the sum of these two is actually probability A, right? Because probability B. Okay. So let's go through this question again, because I think this is super important. So I want you to make sure that there's no confusion. Okay. Now we start with the idea that we know this population is 40%. Okay. So this is, you may ask how we come up with this. This is exactly coming from data. Okay. It's coming from our conjecture. Okay. Looking from data, this is something we know. Okay. And this is some general idea. That means that if I pick up a random guy in the Hong Kong, that say 40% have this. Okay. So there's nothing. Here we have some imperfect medical tests, and those people who study for medicine, some of you might, then actually you know no test is perfect. Okay, so there must be the case that if you're infected, you have positive result is 0.8. Okay, so in terms of terminology, people will say this is that 20% we have a false positive. Okay, you got 20% that's not right, but you don't, but you say you do, it means false positive, right? And uninfected with positive result, oh sorry, 20% is false negative because 20% you don't. And then this 40% is the false positive, right? Because you don't, but you do. Okay, so let me repeat this: 20% is a false negative, and 40% is false positive. But I don't want to put that on a slide because you may confuse it. That's why I don't want to use the false positive, false negative. But if you want to use it, this is what it means. Okay, and later that is what later when we do hypo testing they will call the type 1 error, type 2 error. But let's not introduce that at this moment. But bear in mind we have the same thing. So the question is, if I have a patient who are infected, okay, I want to see what infected. I only give him one test, it's a positive result. Okay, what would be that? So that's very important, right? I have you go to say doctor, and doctor give you a test. Okay, then the doctor will decide how likely it is. Okay, so A is being infected and B is being positive result. Okay, so positive result is B here. Okay, this is B here. This is infected is A. Okay, uninfected is A complement. Okay, so probably A is infected, right? So it's 40% coming from this, right? And if you're infected, your positive result is this coming from here, right? So that's how you get this one, and this is how, that's why you get this one. Okay, so I hope this is clear how we get it. Okay, so we're asking the question, asking this one. Okay, just to, without going to the next slide, so we just look at the question, look at what we're looking at. We're looking at the fraction. Okay, so just make sure that if you forget about what is the Bayes theorem, we start with the idea with conditional probability. Okay, so the denominator will be just what you conditional on, right? And the numerator will be just A intercept B. Okay, so that's the idea. And then you use the Bayes rule, tells you you have to use the multiplication rule again, right? So it's B given A times probability A. Okay, so this one is if you try to look at the graph in the previous slide, this is just the upper branch, the first branch in the thing, right? And this number are there already. So you already know, you try to do it, the numerator is already 0.32, right? Because 0.8 times 0.4, right? What is denominator? Denominator will be just two part, right? B, right? We will use the total probability rule to divide B into two parts. B intersect A plus B intersect A complement. Okay, it's B with A and B with no A. Okay, B can be two parts, B with A and B without A. Okay, so let me do a purple color first. Okay, black color here. Okay, will be B and A plus B without A is A complement. Okay. Okay, and then we again can use the same concept, right? The first term is same as the numerator. Okay, that's why it's 0.32 plus something, and denominator is B intersect A. Sorry, I just run around, but B intersect A complement will be just B given A complement times probability A complement. Okay. What is this part? The first element is already there, is 0.4. Okay. What is second element? A complement. A is 0.4. It's here, right? A is 0.4. So A complement will be 1 minus 0.4. So just 0.6. Okay. So it's just 0.24. Okay. So plus 0.24 here. So that's why it's over 5.6. Okay. So this is exactly we have done, but so that is without going into that. I just show you how we can do it. I hope it's clear because it's not that complicated, right? Just like going into here, it's just like the above branch is 0.32, the third branch is 0.24. That is how you get the answer. Is that clear? I hope that is not very complicated. But of course, this you pretty much would, of course, need an exercise to make sure that you understand. Okay? Is that okay? Any question? Is that okay? Is there any question? If no, then I just erase the thing. Okay? If there's no question, then I would. Is there any question? Maybe let us do. That's okay. I think that's okay. If any question, they ask me. So the next part of this is we need to talk a little bit about counting. Okay, and this is if you learn mathematics, this is what we call combinatorics. Okay, so if this is something, if you learn computer science, that will be part of the discrete math. Okay, and you may ask why we need to do that. Okay, and how to count things is important because later when you do some sampling, okay, posing a coin, that we will rely. And in fact, later actually you see we will introduce a term that will use it for the next topic. Okay, when how about binomial distribution? Okay, that will be something we will need to use it. So that's why we need to introduce here. Okay, and this counting is important for classical probability problem. Okay, because classical probability problem is talking about long run frequency, right? Repeating certain experiment, and when you try to calculate probability, that will be certain kind of counting. Okay, although in our class it's not a math class, we do not do complicated counting. But you can imagine you try to look at the statistics textbook, they will talk to you something complicated question like you have a deck of 52 cards. What is the likelihood that you get a certain kind of style, right? Then especially this would be important when you try to play Texas Hold'em. This kind of show hand or what kind of whatever, that would be important. But let us very simple. We talk about three things: principle of counting, and then we do permutation and combinations. Okay, so basically the three things, and this three thing is important because it related to sampling. Okay, at the last slide we talk about. Now let's start with counting. So we will have what we call the principle of counting. That's very simple. Suppose we need to have a mission the mission have two different tasks. Okay, you do it sequentially. Suppose do it sequentially. Okay, and how many ways you can compete? Okay, the question here is if there's n one way, n one is an integer, right? Maybe 3 ways to do the first task, and 4 ways to do the second task. How many ways to complete the whole task? It's just multiply together. Okay. Actually, we have implicitly have this is we roll a die twice. Okay. There will be 6 outcome for the first row, and that's 6 outcome for the second row, right? So that's why total number of possible outcome is 36. Okay. So this by mathematical induction or some terminology you can think is if there are k tasks, if ni way to do the k task, then just multiply together. Okay. So basically you can see this one is same as y multiplication. It just lists a table, right? Because for each way to do the first task, there's n2 way to do it. Okay. Because the n1 way to do the first task, that's why multiplication. The same idea goes on. So let's see the example, then try to convince you that's correct. Okay. So this is something I used to think when I was a student. Okay. And you go to the Chongqing College canteen, right? One of the cheapest meal when I was a student is like this. Okay. You choose 2 dishes, either rice or noodle. I think noodle is spaghetti at the time. I don't know whether it still exists. I think it still exists. It's the dish when you eat, you don't have money. So so-called 退飯. Then this is the thing first, and second, you will choose one of the main dishes. Meal is pork, beef, or chicken. Okay, and then the three different sauce. Okay, black, white, and red. Okay, so this is something when I was a student 10 years ago. I don't know this exists, but it's one of the cheapest. At that time when I was a student, it was like $10. The cheapest can be $9.90. So it exists in all the canteen in the campus, CC College, NA College, and everywhere. Okay, but I don't know what still exists. I think now it's cost like $20, like double the price. I don't know whether it's still cheap to have it, but when I was a student, I don't have money, so this is something I do. And the question is, okay, because it would be too boring to have the same meal every day, right? So it's fun to talk about this question. Is suppose I ask ourselves how many different ways to eat it, right? So that is actually a three task mission, right? So you have the first task to choose the main dishes, right? And this actually the procedure they do. I don't know if they still do it now, but they would just go there and they will ask you rice or noodle, and then what kind of meat, and then sauce. So that you have 2 different choice for the first one, 3 different choice for the second one, and 3 different choice for the other one. Okay, so that's why 3 times 3 is 18. Okay, so that means that for me, at least I can have variation for at least half a month without repetition. Okay, so that is something that very important, right? So if you try to add a soft drink there may be at least 5 to 6 soft drinks at that time. So probably you can imagine that you can repeat a lot of time without any repetition. Okay, so that is something that interesting thing you would looking at. Okay, so this is counting. Is there any question about counting? So this is something very simple. So we start with something. Okay, this one is also the thing we have is roll a die twice. Okay, and I think we have that at the beginning, right? Very similar question is, what is the probability that some of the phases value is less than 12? Okay, and let's call A is the event less than 12, right? And A complement is no less than 12, right? And each row you have 6, right? Total number of event is 36. Okay, so only one event is A complement, so that's why 1 over 36. And use the complement rule, you have 35 over 36. Okay, So this one looks trivial, right? Simple. But when we talk about drawing the number from drawing card from a deck, then it will be much more complicated. Okay. But that is how you do the counting. I hope that's okay. Now let's look at the next one. So this is a little bit more complicated now. Here is we do permutation. Okay. So permutation and we do combination. Okay. These two, if you learn additional math in high school called M1, then you have learned it. But assuming no one have talked about that before, so permutation. Okay. Permutation is very similar to what we have done here. Okay. Here you can see when I multiply. Okay. And how you do the first task and second task we have been talking about is independent, kind of. All right. So that's why easy multiplication. But when we try to put things, okay, that things can be dependent. Okay. So what it's doing here is you can imagine you have a bed of n balls. Okay. Different balls. Each ball have number on it. Okay. So different ball have different meaning. Okay. So if you try to arrange this ball in a line, okay, how many different ways to do it? Okay. So how to prove it? We will do a principle of counting. Okay, there are n ball at the beginning. How many ways to put the first ball in the first position? N, right? Regardless which ball you're trying to put, there's n way. Okay. Once you put the first ball, only how many ball left? N minus 1. So that's why you multiply by n minus 1. So on and so forth until the end. So that's notation we call factorial, n factorial. Okay. So that is the idea that when you try to have n objects, you try to put in a line, okay, then you have n factorial. Do you note that in here, order matter? Okay. So let us, if you think this is a little bit abstract, so let's talk about this here. Okay. Suppose we have 3 different balls, called 1, 2, 3. Okay. And what we're going to do is we have put them on the line. So there's a phi box or phi location. Okay. So to put the first ball, okay, how many balls you can have is 3 of them. Okay. Maybe you just pick this ball, done. Once you're done, you only 2 balls left. Okay. For the second one. And the last, there's actually no choice. But anyway, there's one way to do it because there's once you put it. So that's why it's 3 times 2 times 1. Okay. And if you don't believe it, you can think about this as a tree diagram. Okay. At the beginning, you have 3 different choices. Right. You can have 1, 2, and 3. Right. Depending on which ball you end up. Or make it easier, we have ball A, ball B, and ball C. So that's make sure that it's not that confusing. A, B, and C, right? And this is the first draw. Once you draw the first ball, A, then what's left is only B and C. Okay. And same, you have the same, you have A and not going to do it, but only 2 balls left, right? And the last draw, only 1 left. Okay. So you can see the last one is always 1. This you have 2 way, and there's only 3 ways. So that's why 3 times 2 times 1. Is that clear how we have n factorial in general? Okay. So I hope that is clear why we have this. Okay. So now let's generalize this. Okay. We don't put all the ball on the line. Okay. We only take out our different balls. Okay. Our different ball. So what we're going to do is, because that's our way, so we will put first one is n, the second one is n minus 1, and n minus 2 until n minus 1. Okay. But this one is actually looks complicated, but maybe I write in this way that it'll be more easier to see, R minus 1. Okay, because you start from 0, the R of them, that's why end up is R minus 1. Okay, so this is the notation, and you can rewrite it as n factorial over n minus R factorial. Okay, because you can keep multiply the n, but this is same as n minus R factorial. So I see some of you doesn't believe me. So let's open another one. Okay, so what you have n times n minus 1 times da 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 times n minus R minus 1. Okay, the R totally they are R term, right? You start from 0 and then you have R minus 1. Okay, so what we're going to do is do the following. Okay, you can keep multiply, right? N minus R da 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 up to 1. Okay, and we have n minus R times n minus R minus 1 and da 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 up to 1. Okay, so you multiply the same thing in the numerator and denominator, same thing happened, right? So and then the numerator is just n factorial because you multiply 1 up to n, right? And the denominator is just n minus R factorial because you multiply 1 up to n minus R. Okay, and since this notation, this expression is often used as a notation for that, that is called NPR. It's called n permutation R, okay, or NPR. So this is the, if you use the calculator, the scientific calculator will have this for you. Okay, so that is called NPR. Okay, basically just like you have n object, you only take out R and order matter. Okay, 1, 2, 3 is same. ABC is different from CBA. Okay, is that okay? Okay, I hope. Now I convince you this is the appropriate thing. Okay, so the question of this is often happen is have a sandwich. Okay, so this question comes out from my experience as well. Is also there's some activity, there's a meeting with the order sandwich. Okay, and we're asking how many different type of sandwich we can make, right? The thing is you have different bread, okay, and you choose some ingredient over it. Okay, and they're asking how many way to do it. Okay, and the thing is like you have to choose exactly 2 different ingredients. Okay, you can have different bread, okay, white, Italian, or whole grain, right? Or you can have different things you want to put in, right? Vegetable, beef, egg, chicken, tuna, tomato, right? But you can't have 2 egg or 2 tuna or 2 tomato. I mean, either you can mix up to make something. Okay, and because sandwich is a stacking, right? So if you put beef above chicken, will be different from chicken above beef. Okay, for some people they will be different, right? Because the sauce from the chicken can go to beef but not, right? Because of gravity. Okay, if you make the sandwich in the space, probably doesn't matter. Okay, because as long as with earth, the gravity, right, the sauce of egg can go down, right? Same as tuna or tomato, right? Some people would prefer different. Okay, if you think they're the same, then it's other issue. But let's say you think that they're different. Okay, if you think they're the same, doesn't really matter order, then we'll talk about this in the next slide. The question is how many different ways to make sandwich. Okay, so you have to do 2 things here, right? You have to choose bread. Okay, so that's why how many different ways you have 3. Okay, because regardless of how you choose the ingredient, there's only 3 ways. Okay, and that's 6P2 is the way you would try to combine. Okay, and I said order matter, so that's why 6P2. Okay, 6P2 is just 6 times 5, right? So that's why 3 times 6 times 5, so 90. Okay. So there are enough way to make different sandwich. Okay. Is that clear? Any question? If no, then we go to the very last one before we break. Okay. So we have a combination. Okay. Combination. Combination simply mean that I take out from N ball to R ball. Okay. The R ball, the order doesn't matter at all. Okay. I don't really care. Okay. And if you think the sandwich order doesn't matter, okay, that is something we need to do. Okay. So what we're going to do is divide them by R factorial. The reason why is because for each permutation you have, right, the R objects can rearrange themselves. Okay. How many you rearrange them is R factorial. Okay. But that is actually RPR. Okay. So this is R factorial. This is just RPR. Okay. And that this expression we'll call NCR. Okay. If you don't like this idea, you can think of the other reverse way. Okay. If you try to do things unorderly, which is NCR, right? And for each combination, you can rearrange them. So which is R factorial. Okay. So that you end up in the same idea, NPR should be same as R factorial times NCR. Okay. So regardless of what you think, you get the same formula. One way is to start with permutation, because overlapping, everyone is overlapping by N factorial, you divide them, you get NCR. Okay. Or start from NCR. For each combination, okay, you can rearrange them by R factorial way. So that's why you're NPR. Okay, regardless of what you do, that's what we have. That is the NCR. So let me give you the example. That's it. Okay. So this NCR will be important because we use it in the next topic. Okay. So that is the main reason we talk about this here. So NCR will be something important. Okay. So this is the question you have when you go to local restaurant, 茶餐廳. Okay. 茶餐廳. So Hong Kong special. You go to there, you go to have a lunch, set lunch there, usually like this, right? Either rice or noodle or even rice noodle, right? And then you have 4 dishes, right? With sausage, spam, ham, and egg. Okay. I don't know now, but in the old days, one very important dish you have to eat before you have the exam is you must have 1 sausage and 2 eggs. Why? It's 100 points. So my mom used to prepare me for that. So whenever I have exam before, I ask her to prepare, but that's important. So there's 2 different types of sauce. Black sauce and white sauce. Okay. So the question is, if you go to this restaurant, right? How many different types of breakfast you can have, right? So there will be 2 different main dishes. Okay. And I think you don't distinguish whether egg or sausage egg because you put on the same bowl, right? Whether left or right doesn't really matter because on the bowl, right? So you rotate the same thing, okay? And 2 different sauce. So that's why you have 2 times 4C2 times 2, right? 4C2 is 4 times 3 and 2 times 1, okay? So end up is 24. Okay? So this is how you do the counting. Okay, so I promised a break, so I just break here and I have a few slides left and then we can talk about that after the break. Okay, let's have a break. Yeah.
So this branch is AX, and the denominator is A over this is yes. The same thing, right? Then if you want to As long as you are in the different way to yes. Yeah, it's yeah. Maybe you can try something first to what is like otherwise it's something. I want to work on it because otherwise. Well, yeah, Yeah, I mean, as I said, the only last
So guess I should resume. I got an interesting question from some of you, telling me that I mean, of course, probably some of you would also have this question is when I write the say NPR, some of you told me that in the high school they learned this one. This is the way sometimes they write. I think it doesn't really matter, you right? I mean, I just don't put it in this way, but it's also okay. I mean, I don't have any thing to say. So one more thing I want to talk about is some of you actually is doing the assignment during the break, and some of you asked me whether how to do the question 3. Basically, I just need the formula. Okay, so suppose you want to calculate the sum of this, right? You can just simply write the sum. 1, 5, 4, 6, 5, 7. Right? Remember the equal sign, then that will be the answer if you want to calculate the sum. Okay. Of course, if you want, you can. You don't need to. I don't need the answer. This is the formula. Okay. Is that clear? Is that okay? Okay. But anyway, I don't want to talk too much about the assignment, but since some of you have already doing it, so I'll be good. So lastly, I'll talk about this, tossing the coin 4 times. And this is something actually prepare us to do the next topic, what we call the binomial distribution indeed, okay? So this is, we're doing an experiment. In particular, we have 2 outcomes, tossing a coin. So that's why later we see what is the binomial, but we just wait for next week to talk about that. And here is I toss the coin 4 times, okay? And the question is, what's probably exactly 2 tails? Okay, so how to do this is exactly 2 tails. That's a little bit difficult because we don't really care where the tails appear, right? Maybe the first time you have, second time you have, right? Or the first and the third, or so on and so forth. There are many kind of possibilities, right? So how can we work on it? Okay, so first, we to consider what is the sample space here. Okay, how many outcomes are here? Okay, so we actually can think about this by thinking about the principle of counting, right? Each toast you have 2 outcomes. Okay, so that's why you have 2 times 2 times 2 times 2. That's 2 to the power 4, 16. Is that clear? 16 because each toast you have 2, so it's, and then you do this 4 times. Okay, now the next part is a little bit complicated. Okay, this how many outcomes that you have two tails or two heads is actually related to the idea of pulling a ball. Okay, so let's think about this in the following setup. Okay, let me have a picture here. Okay, so instead of thinking about how many toe, okay, let me go back. Let's think the following. Okay, so let me go back to what I'm doing now. So what I'm going to do is I'm going to draw two balls out of 4-ball box. Okay, and the ith ball drawn is being the ith toe. So what I'm talking about is this, like this. Okay, what we are talking about is we have a coin. Okay, it can be end up with head and tail. Okay, and you try to repeat this 4 times. Okay, so instead of thinking about this, okay, we think about this in the following way. We consider there are 4 balls here. Okay, the first ball is 1. Okay, the second ball is 2. The third ball is 3. The fourth ball is 4. Okay, so we are going to pull 2 balls out of this 4 ball. Okay, so if I have ball 1, 2, which means that I have, suppose it's head, right? So this means I convert it to head, head, tail, tail. Okay, if I have 1 and 3, okay, that means I have head, tail, head, tail. Okay, if I have, say, 2 and 3, then I have tail, head, head, tail. Okay, so each outcome where we have 2 heads, okay, is same as I draw 2 balls from there. Okay, and I draw 2 balls from there, which means that an order, right? 2, 1 is same as 1, 2. Okay, so that's why how many of this is just 4C2. Okay, let me repeat this again because this is a little bit complicated. Okay, so we have head or tail. Okay, 2 outcomes. Okay, and we know how many total number of outcomes you have is 2 to the power 4, right, which is 16. Okay, so the question now is we're asking how many outcomes that actually involve only 2, I don't know, 2 head or 2 tail, or 2 tail. Okay, 2 tail, sorry, it's 2 tail. Okay, so I should be, it's 2 tail, so I'll just change it, just make it head. But so I would say if 1 is putting in the ball here, means the first one is tail. Okay, so we have tail, tail, head, head, and I have tail, head, tail, head, and I have head, tail, tail, head, right? So if I put all the 2 balls, all the arrangement of 2 balls, then I get all the possible case for the 4 toes. Can you see that? Okay, so we'll be doing this in the next class, but this is end up is 4C2. Okay, and 4C2 is just the following, right? 4 times 3 over 2 times 1, which is 6. Okay, it's 6 over 16. So that's the answer. Is that clear what we are doing? So a little bit tricky, but don't worry, we'll come back to this when we talk about binomial, but you'll be doing assignment question later, but that will be the same, similar to what we have here. Okay, so that's why we have 4C2 here. Okay, is that clear why we have 4C2 here? Because just like thinking 2 outcomes there, it's just like drawing, you have 4 different balls, you can draw them out. Okay, Is there any question? If no, then we just almost end this one with why we care about this, because it's closely with the sampling. Okay, so if you sample without replacement, you will be, what we're trying to do is relay principle of counting. And if we order the sample without replacement, we just keep doing things. That's same as permutation. And unordered sample without replacement, then will be combination. Okay. Sorry, that should be. So there's a typo. It should be with replacement. Sorry. So because it just keep multiply itself. Okay. But anyway, you will be you will know more later. I guess it's not a big deal for the moment. I guess what it left is, so these are all the video. You want to look at it if you miss anything from the slides. So what left is I want to show you the very last, there's 3 spreadsheet function that you can use it to calculate permutation, combination, and factorial. So I'm not going to go to Excel to show you this, but this fact is just factorial. Permute, NR is just NPR. Combine is combination NCR. Okay, so I'm not going to go to the Excel and do it. I mean, you can just try it for yourself. I mean, it's not particularly important. Unlikely we're using it, but just showing you that it can be done in Excel. Okay, in case you don't have calculator in your hand. I mean, I guess now you don't have calculator anymore. But if you really want to calculate, then this is how you're going to work on it when you work on assignment. That's how you do the Excel thing. Okay. Is there any question about the probability? So just a 1 minute or 2 minute review what we have done so far for this topic, right? So first we just define what is probability as a ratio. And after that, we define probability as an axiom. And the only different thing is axiom 3, which is something not implied directly from the classical idea. And then we have different rules, complement rule and total probability rule. But the most important rule is the base rule. It's the base rule here. And you should know very well how to understand that. And after base rule, we learn today permutation and combination. And they will be important as we talk about random variable. Okay. Is there a question? We've done. And because of the delay, though we don't give you the assignment yet, we will, after the assignment is done, I will release the assignment 2. And again, you give you around 10 days to finish. So I will just release after it's over. Unless you want me to release earlier, but otherwise I would just keep it once you're done. Okay. Or at least I will wait until the other class finish the whole thing I will done, but the deadline will be the same 10 days after the first assignment. Okay, so you always allow 10 days to work on it, at least 10 days, maybe more or less, but okay. Is there any question? If no, then we talk about random variable. Okay. Random variable. Okay. Any question before we start? Okay. So random variable is a very interesting thing. Sometime after you learn the first stat course, you go to the second class of statistics, you may not understand what's going on with random variable. Okay. And you may think random variable is a variable that's random. Okay. And indeed, that is not entirely correct. Okay. Random variable is not just a number that is random. Okay. It's not a number that is generated by a computer, right? Rather, random variable is just simply a function. Okay. What function is for any outcome for random experiment, we'll give a number. Okay, we just give number to outcome of random experiment. That how you put number to an outcome is what we call random variable. Okay, so that start the random variable is a function. That's important. It's a function, so it's not variable. It's a function. It's the way how you assign number to outcomes of random experiment. It's a number. Okay, that you assign to it is the way you assign number, not number itself. It's a random variable. It's actually a function. Okay, and you want to ask why that's the case. Okay, why we need a number. Remember at the beginning, or just we did in the previous section. Why it's important? Because remember, look at the very last example we have is if you toss a coin 4 times, the sample space is 16 outcomes. Okay, and if you toss it 10 times, okay, what is the number of outcomes? It's 2 to the power 10. Okay, 2 to the power 10 is a very large number. If you don't believe it, let's Excel it. Okay, okay, Excel is not coming out. So let's do Google. 2 to the power 10 is 1,000. Okay, so you have to look at, anyway, 1,000 outcome. So when you do calculation, it's very complicated. And very often, we don't care about the order, right? Because it's complicated because the order matter, right? You have toss and coin, right? If you don't care about the order, right? You just care about tossing a coin 10 times. You just care about how many times you get a tail. Okay, you only have 11 possible outcomes because you only have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11 possibility. Okay, so instead of 1,000, you only care about 11, right? So it's much easier to work with. Okay, so but there's some benefit. You simplify the you change the sample space, or you change it a little bit, right? Change the number instead of the order matter, you change number, right? From 0 to 10. There's some complication issue is before each outcome is equally likely, right? But now when you simplify it to say 0 to 10, it's no longer equally likely, right? So it reduced complexity, but it also introduced something difficult thing to handle. Okay, but at least things with the worry is much easier. Okay, so basically random variable, just to remind you, is just to reduce the complexity of the world we're looking at. Okay, something is irrelevant for our purpose, we just take it out. Okay, so the next thing is what is support of random variable. Okay, this is exactly the idea of sample space in the random experiment. Okay, sample space in the random experiment is all possible outcomes of the random experiment. Okay, so random variable is a number, right? Mapping is coming from, you tell me the outcome, I give the number. Okay, the support is what kind of number you can put in. Okay, so in the case you toss it 10 times of the coin, right? And you just care about number of tail or number of head, right? Number of tail. Then the support will be just 0 up to 10, right? Because there's no tail, 1 tail, 2 tail, 3 tail, up to 10. It's just like the support is 0 from 10. Okay. And in many cases, the random variable or the event is actually a number. Okay, so that's why things become easier very naturally. Sometimes not so natural. Okay. And it's very important to distinguish what we call discrete and continuous random variable. Okay. The reason is being that when discrete, you can use the math you learned in high school without any problem. Okay. With continuous, okay, we need to rely on calculus. Okay. But don't worry, in this class we don't need to use any calculus. Okay. Only appear in some expression. Okay, and for our purpose, you just think Integration, when you see, it's just summation. That's it. Just adding, okay? Because integration, in roughly speaking, is just basically summation, just adding things, okay? But you have to add many things together, so that's why something complicated, okay? But just to introduce the idea, the different, let's see the example, okay? And when we have discrete random variable, is when the support is finite, means that the outcome is finite, okay, naturally finite. Or you have discrete, but just you count integers, is also finite, okay? How many customers coming to the store can be 0, 1, 2, 3, 4, 5 up to infinity, right? Although it's infinity, it's still a discrete, okay? And what is discrete means is you pick anything, okay? You take an average. Is it still meaningful? Okay. If it's not meaningful, then it's not continuous. It's discrete. Okay. Usually, when you take two numbers from the random variable, if still makes sense, then it's the continuous. Okay. But of course, the definition is like this. It's like what we have here, and we'll talk about discrete random variable in this topic, but afterward we'll focus everything on continuous most of the time. I mean, we'll actually for two things. We'll talk about binomial and continuous, but discrete is still, discrete is still important because we still talk about that when we talk about proportion. Yeah, but underlying when we do calculation, most of the time we will use the continuous random variable to approximate the discrete version. But anyway, you'll see later. Okay, let's see the example here. Okay, I toss a coin once. Okay, the sample space is just head and tail, right? And what is random variable? Okay, the way I do it is just I say total number of head. Okay, I can do number of tail, doesn't matter, just because the same thing, right? Because only two outcome. And number of head is x. Okay, here we have x equal to 1 when we're head, right? X equal to 0, we have tail. Okay, so why this is a function? Because when you have head, I map to 1. I have tail, I map to 0. Okay, so the support of x is just 0 and 1. Okay, so basically, just to repeat what we are doing in the sample space, okay, it's just head or tail. Okay, and x it just end up with 1 or 0. Okay, and x is just map, just say telling you how you from the sample space to the support of it. Okay, okay, there's mapping here. So okay, is that okay? So next, you see the benefit of doing it is if you have sample space of tossing a coin twice, it's either head tail, tail head, or tail tail. So you have 4 outcomes. Okay. Now you consider the case we have random variable of total number of heads. Okay. So what remain is we either have 0, 1, or 2. Okay. For 0, it's just tail and tail, right? For 2, it's just head and head. Okay. And if you have head tail or tail head, it's just 1. Okay. You may ask what is it doing, right? Because when you toss many times, that will be easier. Okay. And random variable formally, we just say it's a function. So this is 1, this is 0, and this is just 1, and this is 2. Okay. And very often, because we are lazy, okay, we will usually just say, we don't forget about this guy. Okay. We will just say x equal to 0, x equal to 1, and x equal to 2, right? We just don't write what is inside, right? But you know, this is saying as this is t and t, right? This is saying as TH or HT, and this is just a head. Okay, so that is, we're trying to give numbers to outcomes so that we make our life easier. Okay, instead of having things that have no relationship, potentially different outcome, don't have anything, we focus on things that have some structure there. You can easily study. Okay, because probability, what are the possible outcome can be a lot of difficult thing. Okay, but when you convert to number, okay, and naturally things become much easier to handle. Okay, so that is the reason, and naturally arise that many things that we can have a nice form. So that's why this is a very useful way to handle things. Okay, is that clear? Okay, and when you have continuous random variable, when you use it, that means continuous random support is infinite. Okay, that is very natural. When you talk about outcome, that is actually a lot of possible outcome infinite, like temperature, right? When you try to measure it, is continuous. Okay, and look at the stock market index. Okay, you may think the stock market is the index you have is like it's a finite, right? Because number of integer or number of decimal places you end up is like finite, right? But because the number of outcome is so big, right? Assuming it's continuous actually has no loss of generality. Okay, because there are so many outcomes there. Assuming continuous is a good approximation. Okay, so you can imagine that although technically you need an infinite thing, okay, but when outcomes are so many, right, and it's okay to assume continuous. Okay, even though what we observe in the real world philosophically having a discrete, right, but when outcomes there's so many, that continuous is a good approximation, right? And actually that's what we do the bell curve, right? When you learn there in high school, bell curve, right, is we apply to almost everything. Our height, our weight, our IQ, everything bell curve would fit, right? But all those measurements are, I mean, strictly speaking, a discrete measurement, right? So, but as long as things are many possible value, then you can use continuous and a shortcut. And that is a good shortcut. I mean, so far I've been thinking. So that is the idea. So it's the stock price, a temperature, or other thing that is a good. Okay. So now some example here is the temperature. Okay. The sample space you have is X is a real number that is bigger than this absolute zero. Okay. So if you just care about the measurement of temperature, then automatically the sample, the random experiment we have here is exactly same as the random variable. Okay, so there's no need to simplify the sample space because the sample space we have already is the temperature. Okay, but suppose you care about the climate as well, but you only care about the temperature, then you just simplify. Okay, because what we observe today's weather is more than temperature, right? You may have humidity, you may have sunshine, UV index, so on and so forth. But if you only focus on temperature, you forget about other things as well, then that's the case. Okay. Now the next one is stock market index, right? Same idea. If you only focus on index, then it just from positive number, right? Non-negative number. Okay. But do note that what we observe, right? The real world is not the stock market index, but what we observe actually is the stock market movement, or the whole stock market. But we just summarize it as the stock market index. Okay. In that case, it's simplification, right? Because we don't care about whether stock A goes up, stock B goes down, stock C goes up. We care about the, say, Hang Seng Index or Dow Jones Index or SP 500. Okay. In that case, it's a simplification of the complicated environment we are facing. Okay. So we summarize it into a single number. Okay. And some of you would ask, okay, why just one number, not two number, right? You have Hong Kong stock market, US stock market. right? You have X share, many things, okay? The thing is, we are introductory class. We are unable to handle more than one variable, okay? Just one variable. If you want more, other class. Sorry, just one variable, okay? So, but the reason why more than one variable is much more complicated, so we can't really handle it an introductory. But so that is it. But for those who are studying the quantitative finance QFN student, you probably need to look at how you handle more than one variable, because that's important, and how to swap. Okay, and it's not our class to cover it. Sorry about that. To cover it is very complicated. Okay, you need a lot of difficult things, but anyway. But all the concepts are similar. Just the calculation is much more difficult. Anyway, so let's get started with some discrete random variable. Okay. So we'll start with some description over it. Okay. Now remember the last class we talked about random experiment, sample space, right? And we can do it in the Venn diagram. Okay. Assuming everything is equally likely, then the Venn diagram is a good description of everything, right? But now when you collapse everything in the number, right? And the classical idea that every outcome is equally likely is not going to work, right? And you can imagine toss a coin problem, right? If it toss a coin many times, okay, and X is going to be somewhat intermediate value, right? It's unlikely to be 0, right? Unlikely to be very big, right? Somewhat in the middle, okay? So it will be the thing that not every number will be equally likely, right? Just look at the example what they have here, right? 0 only have probability of 1/4. X equal to 2 is a quarter. But X equal to 1, the probability is 1/2. It's more likely in the middle than on both sides, right? So it's not equally likely. So how can we describe this kind of situation? Okay. So we will use the idea, what we call the probability distribution and cumulative probability distribution. Okay. Sometimes people refer there's a shortcut. This is what we call the PF or PMF or sometimes PDF. Okay. And this is sometimes called CF or CDF. Okay. Just people being lazy when you talk about the shortcut notation, but so we will just use big YP. This is probability function. Okay. It just take the first and second. And Y your PMF, PDF, M refer to the mass, probability mass function, and M, D is the distribution. Okay, D is already there. Okay, CF the same is cumulative function, or cumulative distribution function, or cumulative probability function, CPF. But anyway, so this is when you look at the textbook, that's something they refer to this. But what are they? Okay, the first one is very trivial. Okay, it's just saying that probability X equal to that value is what it is. Okay, in the example we have P of 0 is 1/4, P of 1 is 1/2, and P of 2 is 1/4. Remember the tossing the coin, right? Because this is just I think this is head, right? And this is tail, and this tail head and head tail, right? So and each one is equally likely, right? So that is how you have the P of X. Okay. The next one is something can be derived from above. Okay. So it's not asking you what exactly this number is. It's less than or equal to. Okay. Look, the equal to is very important. Don't forget the equal to. Okay. And that's adding up, is adding up all the number before it. Okay. In that case, you just try to look at this is F of 0 is 1/4. F of 1 will be 3/4 because add up the two things. and f of 2 is just 1. Okay, we'll give you more example, but just get this idea. Okay, don't worry, we'll give you example immediately, but this is how these things are defined. Is that okay? So we'll give you a more example. Okay, so this is just very simple, head or tail. Okay, and random experiment, random variable is just number of head. Okay, so only two number, either 0 or 1. Okay, and just 0 means what? 0 means tail, head means 1, right? So you know they're equally likely. Okay, so P of 0 is actually asking this, right? This number is exactly probability that, right? We have a tail. Okay, and this is actually probability with a head, and we know this is a fair coin, so they're same, right? Because they are 1/2. Okay, and f of x, right, is asking you that what is the value, what is the probability that x is less than or equal to 0, which is this 1/2, right? This asking what's probability that x is less than or equal to 1, right? Less than 1 can be only two values, 0 and 1, right? Just add up together, right? So just 1/2 plus 1/2, that is 1. Is that clear? Is that clear what's going on there? Is that okay? So it's easy to look at in the graph. So let's look at the graph. I actually will draw it later, but if you try to draw the graph here, P of x is 0 and 1, right? Then you have 1/2 here, 1/2 here, right? And if you try to draw the f of x, okay, will be just, this is 0, that is 1/2, okay, and 1 will be just 1. Why? Because you just stacking the two to here. Okay, here is just stacking anything before it. Okay, you just, one is here, the other is here. Okay, just stack. Maybe I just do the color. This is here, stack. Maybe just do this one. Just stack it out. Is it better? Just stacking. Okay, just stacking up. And you probably ask why. We ask why we care about f. Okay, because shouldn't p be sufficient, right? The reason we will talk about next class is when we talk about continuous distribution. Okay, it's only reasonable to think about f. P is hard to think. Okay, if you are not learning physics. Okay, that's density thing. But f is the reasonable thing to think about when we're continuous distribution. Okay, because no point talk about particular value. Okay, so that's why I talk about both. But for the main purpose, we just need to think about p. Okay. Now let us finish this thing. Okay. By the two examples, then probably we are done, and then we will just leave the expectation for the next class. Okay. So here I told the coin twice. Okay. So there are all 4 outcomes, 2 by 2, right? First head or tail, second head or tail. Okay. So we have 4 outcomes here. Okay. If you don't believe me, you can just do a tree diagram, right? First time is head or tail. Second time you have head or tail, and then you have head or tail here, right? So you have head, head, tail, tail, head, and tail, tail. Okay, so 4 outcomes, and each outcome is equally likely. Okay, and what we're trying to map this is number of head, right? So this is equal to x is 2 here. This is x equal to 1. This x equal to 1, and this x equal to 0. Okay, and x equal to 0, what's probability here? It's just this branch, right? Each branch is 1/4, right? So that's why 1/4. Okay, it's just this guy. And x equal to 1 is actually referred to 2 branches, right? One branch is 1/4, 2 branches is 1/2. Is that okay? And finally, we have x equal to 2, okay, which we have only one branch is 1/4. Is that okay? So we can actually draw this diagram, right? Is x equal to 1/4, 1/2. Oh, sorry. X is only have a value of 0, 1, or 2. Okay. And P of x is just 1/2, but 1/4, 1/2, and 1/4. This is 1/4, this is 1/2. Okay. So this is the graph looks like, right? And let me use 3 different color. It's red, purple, and then blue. Okay. And then how you can get the big F, right? Just very simple. 0, you still have the red. Okay. And for 1, okay, you have red here, but you also have the purple here. Okay. And for 2, okay, you have red here, purple here, and then blue here. Okay. So what you left is this is 1/4, this is 3/4, and this guy is 1. Okay. Is clear? Is it clear how we derive from this? Is that okay? So I think that's the end for today. We will see you next week. I hope that's okay. So have a good evening. I'll see you next week. Is that okay? Okay.